Okay, so time to learn about the synthesis and reactions of carboxylic acids. So you've done a lot of the synthesis of carboxylic acids already, but it's always nice to have a good review. So let's get started. So the first one is oxidation of alkenes. So here in this one, you cannot take a completely substituted alkene. You have to take an alkene which has hydrogens on it, and then you treat that with KMnO4, and it will cleave the alkene to give you two carboxylic acids. Now, depending on how many carbons you have, is the type of carboxylic acids you will get as well. So the best way to do this is to take a symmetrical alkene so you don't get two different kinds of acids. So you don't have to separate them out, okay? But otherwise, it's the easy way of making carboxylic acids. You can do the same thing with alkynes. So alkynes also, now you can treat with KMnO4, or you can do ozonolysis also on this. Okay, so either of those two reagents will work, and also you will get carboxylic acid. So again, there is a cleavage of the triple bond here. Again, you may want to choose an alkyne that is symmetrical so you don't get two different carboxylic acids. Then here is the oxidation for primary alcohols. Remember, not secondary. Secondary will give you something different. So yeah, they give you ketones. So if you take a primary alcohol and then you treat it with KMnO4, then you get a carboxylic acids. I hope that even within these three, you can see a common trend here. KMnO4, 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 right? Because carboxylic acids are the most oxidized groups of all. So pretty much all we're doing is oxidation, 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 for every reaction. So let's continue on from here then. And here is another oxidation. So you can take an alkyl benzene, whatever alkyl group you have, no matter how small or big, treat that with KMnO4 and you get carboxylic acid. This is also called degradation, right? So you just remove the whole carbon chain and you get benzoic acid, no matter how big the alkyl chain is there. Oxidation of aldehydes. So I'm taking all these functional groups one by one for you, okay? So aldehydes, again, you can oxidize them with KMnO4. You can't use a weak one here, okay? So you can't use PCC, and you can see that I've not used PCC anywhere. I'm using strong oxidizing agents for all of these reactions. So KMnO4, and then that will also give us carboxylic acids, okay? So that's with aldehydes. And then this one you have done, but let's go ahead and talk about this. So this is hydrolysis of cyanohydrides, and also with nitriles. So you've run this reaction before, so I thought I would just kind of remind you that if you take an aldehyde or a ketone, you treat that with cyanide and you get a nitrile. That nitrile you can hydrolyze to give carboxylic acid. So this is how we learned it in aldehydes and ketones, but you don't have to have an aldehyde or a ketone to do this reaction. You can just do an SN2 reaction with any kind of an alkyl halide, get a nitrile on there and do a hydrolysis, okay? But the one thing you have to remember as you're doing the nitrile reaction is that you're adding a carbon. Okay, so here 1, 2, 3, 4 carbons, but here 1, 2, 3, 4, 5 carbons. So by adding a nitrile group, you actually add a carbon. So you have to remember that you have to add one more carbon at the end, okay? Or you are adding one more carbon, okay? So you start with one carbon less. In case you want to make pentanoic acid, you start with something with 4 carbons, something like that. So you have to remember that, okay? Because that's kind of what this reaction does with the nitriles. But again, not an old reaction, or I should say this is an old reaction. You have done this before. This is a new one, okay, for us, and this is with Grignard. I mean, you've done Grignard before for sure, so that's not something new. But this reaction itself is a little bit new. So what you're doing is you're making the Grignard just like usual, which is an alkyl halide with magnesium. And once you do that, then if you add carbon dioxide to this followed by hydrolysis, then you get a carboxylic acid. Okay, so that's how you can use Grignard reagent to form a carboxylic acid. Again, you're adding one carbon, okay, and that carbon is coming from the carbon dioxide. So here is another reaction just to show you the same thing, like making benzoic acid. So you can make benzoic acid by taking toluene, any kind of an alkyl benzene, right? And treating that with potassium permanganate. We did that previously, and here is another way of doing it now. So, just a variety of things that you can do. So in any case, I just want you to note again for all of these reactions that we did, that a lot of oxidation was going on, right? Potassium permanganate. So strong oxidizing agent was used. So now for the reactions of carboxylic acid, they're not going to be that many, so I'm not doing any mechanisms in this slide, so very fast to do. But anyhow, some of the most common ones is the acid-base reaction. The other reactions that we are going to do are going to be nucleophilic addition reactions, so which means taking a carbonyl and turning it into a tetrahedral. So you're just adding on things, just like we've done with carbonyls before. So that's something we're going to do, and then we are going to do a lot of interconversions. So remember derivatives, which means that you convert carboxylic acid into any other derivative possible, okay? And then there's one more reaction to cover, which is decarboxylation. So here is the list of all the reactions that we are going to cover. Each one of them is covered in the following slides, okay? So let's just go ahead and do those. This is just for your reference. So first of all, neutralization, you can call it neutralization, or you can just say reaction with the base, whatever it is. But you've done this reaction before, is where you take a carboxylic acid, treat that with any kind of a base, hydroxides, any of the hydroxides, and then you get a carboxylate. So it's a reaction. It's acid-base reaction. Anyhow, okay, you can turn a carboxylic acid into an acyl chloride by, excuse me, by using thionyl chloride or phosphorus trichloride or pentachloride. And I think I have a little error here, which I will fix, because it should be pentachloride, okay, over here. So you can use either of these reagents. Again, you've done this reaction before, but it's been a while, okay? That was in aromatic chemistry, where we made the acyl chlorides. Now, why would you want to convert an acid into an acyl chloride? And that's something we're going to learn later on when we talk about derivatives, okay? So right now we're just focusing on this reaction, but why we're doing this, we will learn later on, okay? But I mean, I can tell you it's not a secret or anything. These are more reactive, okay? Now you know. Dehydration. So here what we do is we take 2 carboxylic acids, and if you heat them high enough, then you can form an anhydride. And I've shown you all of that in pink, so you can see what are the groups there. If it was all in black, I think things kind of get muddled up, okay? And with carboxylic acids, we are talking a lot of oxygens now, right? 2 oxygens coming from carboxylic acid. And then with anhydride, you still have that 1 oxygen, because once you have the dehydration, which is the removal of water, so that's going to be something like this, right? So this water is gone, and then you're left with an extra oxygen right there. So carboxylic acids will give carboxylic anhydrides when you heat them high enough. Now, this is not like the best kind of reaction to do to form anhydrides, because heating any kind of an organic compound can result in decomposition of that organic compound. But diacids are a lot easier to dehydrate, okay? So what I mean is this one is a little bit easier to make than this one, which means that there are other ways of making it. It just doesn't mean you use this method. You can use something else, okay, to make an anhydride. So we will do that also, okay, later on when we get to the carboxylic acid derivatives. So then another reaction of carboxylic acid is converting it into an ester. So that's also a derivative of carboxylic acid. So you take an acid and an alcohol, treat that in presence of an acid. Anything like sulfuric acid works usually as a catalyst, and then you end up getting an ester. An ester is where you have the H of the carboxylic acid replaced with an alkyl group. Okay, that alkyl group is coming from the alcohol then. So that's kind of what's going on over here with esterification. Then there's decarboxylation. Decarboxylation is loss of carboxylic group, which is CO2. So again, high heat. Okay, so again, you don't want to really do this because it's really very bad for the organic compound to heat anything so high. But this can happen, and if the compound can be heated that long, then the decarboxylation can occur, and you end up getting an alkane. Okay, so what's happening in the process is you're losing a carbon though. Okay, so this is the opposite of carboxylation. To form carboxylic acid, this is decarboxylation, to remove carbon dioxide. And finally, you can take a carboxylic acid and you can reduce that to give an alcohol. And these ones you only get primary alcohols because carboxylic acids are terminal groups, so you only get primary alcohols. Okay, so you can use lithium aluminum hydride, or you can use borane also to go all the way to alcohol, and that's reduction by using a very strong reducing agent. If you didn't want to go all the way to the alcohol, you want to go to aldehyde, then you choose a different kind of reagent. And again, we've dealt with this before, so I'm not giving you the structure here. You can look at aldehydes and ketones synthesis, okay, to find the structure for DIBA. The name is given here, diisobutyl lithium hydride. That's the structure, and that's not a very strong reducing agent, but it's stronger than sodium borohydride. So you use DIBA to reduce the carboxylic acid to an aldehyde. Okay, if you use a very strong one or BH3, then you can go all the way to alcohol. Now, why do we use borane here? Borane is used over here is because lithium aluminum hydride can reduce other functional groups also. So what if you don't want to reduce other functional groups? Then you tend to use borane. All right, so you have to be careful when you have other functional groups, like what kind of reagent you want to use is something you have to kind of think about. Okay, but there are 3 reducing agents for giving you 2 different kind of products. I think that's it. And I think that's it. Okay.